Yeah, thanks so much. So I put up my plan for the talk, and let's hope that I can do it and that I have reserved plenty of time for point 4. So I want to do a recap, which I've already put on the next slide, so you can kind of review what I believe we've discussed so far, the most important things. I'm going to talk about now that you've got these bases of symmetric functions, you will really want to work on the product because, hey, the product encodes the reduced Kronecker coefficients, or at least I haven't proven that yet, and I will. Then I'll get to, I hope, a combinatorial interpretation for the reduced Kronecker coefficients. And it's complicated because we encode it in Tableau, and the Tableau have entries which are multi-sets. And so there are lots of little conditions which try and capture the Littlewood-Richardson lattice conditions that are going on inside of a Kronecker coefficient. And the fourth point that I want to leave extra time for is an ask me anything about Kronecker and reduced Kronecker, because there are lots of questions and people have opinions about these things. And I want to kind of establish what I think this work implies about the Kronecker and reduced Kronecker. So I'm going to give this combinatorial interpretation for the reduced Kronecker, but when it's given by a sequence of rows acting on a single partition, and then the coefficient of another partition, and this is something you just can't do with the Kronecker coefficient. So there's something different about the reduced Kronecker coefficient and the Kronecker coefficient, but these are super closely related. We'll get to that, and hopefully in the AMA. So my recap, I have outlined what I think what are the important points from the 4 days. The first day, Rosa went from the Littlewood-Richardson rule is the tensor product rule for GLN representations, and in the same way, the Kronecker coefficients are the tensor rule for the symmetric group representations. And she talked about the limiting property of the Kronecker coefficients, and she connected these to Schur-Weil duality consisting of GLN and SK, and then Schur-Weil duality was at the beginning of the 20th century. Since then, there have been other centralizer pairs discovered. And in the 1990s, there was a centralizer pair of GLN, or sorry, of SN and the partition algebra. And this is another diagram algebra. And the what she concluded by studying that is there must exist a character for the symmetric group in the same way there exists a character for the general linear group, and that the coefficients of the power sum expansion in the Schur functions are the symmetric group characters. The same coefficients of the power sum in this other basis that must exist are the partition algebra coefficients, partition algebra characters. And then I covered the Frobenius map, which maps the symmetric functions of any degree into the symmetric functions of degree n. And what we're going to do is we're going to map it into degree n, where n is super, super big, so that we can safely take the inverse limit of this map and define the symmetric group character to be the inverse limit of a Schur function. But then on day 3, I gave some better definitions in terms of power sums. I introduced 3 different bases. One is this H lambda tilde, which are the character symmetric functions corresponding to an induced trivial character. So you take the character that's trivial on a parabolic subgroup, and you induce up to Sn, and that's this character H lambda tilde. If you take an irreducible on a degree n, and you an irreducible of a subsymmetric group Sk, and you do induce up to Sn, then you have this X lambda tilde, and then the irreducible character for all big N is encoded in this S lambda tilde. And there's a relationship between these 3 bases, where the change of bases between these 3 bases is fairly well understood using standard techniques of symmetric functions. And then Rosa finished what I was unable to achieve on day 3. Is also, she gave the multi-set tableau expansion of a homogeneous symmetric function in terms of multi-set tableau. And she pointed out that if you take the homogeneous symmetric function, you expand it in these H tildes, that you get multi-set partitions. There's one for every multi-set partition. And I'll review that on the next slide. But before I go on, I want to remind you that on day 3, I had two results that I denoted star and star. There were 2 of them, but they're exactly the same. And it says that a symmetric function identity is true if it is true by evaluating it at enough points. And that's kind of like a polynomial identity has at most, has a finite number of zeros. So I'm kind of using that idea, and I use it over and over again to take its Frobenius image and evaluate it on its Frobenius image. Now, if you've been following along, you may, and you're an absolute expert in this field, you may know that a lot of these things were already reasonably well understood. The centralizers of the partition algebra were kind of known to have a Murnaghan-Nakayama rule. The restriction problem was known by Littlewood to have some scalar product is related to plethism. The reduced Kronecker coefficients were known to be kind of stabilized as n gets big. But I think the innovation here is already that you kind of put them in one object. You connect restriction and Kronecker and partition algebra, and you put them all in one object, and you get, and I want to say you get something out of it. And if we don't get anything out of it, I think this is a complete waste of time. I agree with you, but we get something out of this. And I will show you that you can get you can make some advances on products that we could not do before, kind of having the right way of leading us through the wilderness. And I really think that Kronecker and reduced Kronecker, there's a wilderness, and you just need to just keep pushing and pushing and pushing and pushing, and we will understand those much better if we keep doing that. So the two formulas that I had on the previous page said that there is the H says that something like H21, there's one term for every multiset partition of a multiset. So here my multiset has 2 1s and 1 2. And there is one multiset partition where all of those elements are in a separate part. And so there is one term H21 tilde. Then you can put the 2 1s together, and there is an H11 tilde. You can put them together in a different way. You put the 1 with the 2 and the 1 you keep separately. There's an H11 tilde. And there's one where you put all the 1s, 2s together, and then there's just one part, and so it's H tilde. So I denoted this for a multiset partition. Pi, I denote, is a multiset partition of a multiset 1 squared, comma 2. So I have my multiset, and I indicate that it's a multiset by putting the double curly braces. And I have this weird V dash, which says that, hey, it is a multiset. So that's my notation, is a multiset partition. And I have M pi is equal to the partition of multiplicities. Of the multisets in pi. And then Rosa showed this step, and she also showed the next step, that if you expand the H tildes in the S tildes, there are these, you put them in tableau. So the change of basis coefficients is column strict tableau between the H tilde and the S tilde. And so if you want the S tilde expansion of H, there's one tableau with an extra long row. And the way I draw it, the way we drew it in the paper is, and we continue to draw it, is that this extra long row is as long as it needs to be. But we draw it with just the minimum number of boxes, because we can't be drawing these huge long rows. They would just take up the whole page. So what we draw is we say the blank boxes are the ones that go underneath the part with the content, and then there's this little piece that sits off to the side on all of these other tableaux. So even these are all off to the side, but really there's an extra long empty row off to the left of everybody. And so the S tilde expansion of H21 is S3 tilde plus S21 tilde plus 4S2 tilde plus 3S11 tilde plus 7S1 tilde plus 4S empty tilde. So that is, you remove the first row and you just record the second row and above for the shape. And there's one term in this expansion for each one of these multiset tableaux. So what we're going to do now is, so we saw these multiset tableau coming out of in the coefficients. We could first see it when you do 1 to the n, you have set tableau. And so you're seeing Bell numbers and you're seeing tableau of Bell numbers. And so you just start guessing at what's going on. And then you say, well, what's the most logical conclusion of if H1, if the coefficient of H1 to the n has set valued tableau, what's the coefficient of H mu? What are those objects? And so multi-set tableau is kind of a natural thing which is coming out of these symmetric functions. Then you start guessing it and you have to start proving these things. And it turns out that this feels like the right combinatorial interpretation, at least for what we're doing. Not that there aren't other ones, but let me show you why I believe these are kind of a good way of representing the objects. So first thing I need to establish is that S lambda tilde times S mu tilde is equal to the sum over gamma, the reduced Kronecker coefficient, lambda mu gamma, S gamma tilde. And so proof, this one is using star, we say that the phi n of this equation is S n minus size of lambda comma lambda, Kronecker product S n minus size of mu comma mu, and that's equal to the sum over gamma G mu gamma, G lambda mu gamma bar S n minus size of gamma comma gamma. And because this works for enough values of n, this is a symmetric, the original equation is a symmetric function identity. Okay. But then let's see if we can develop some of these products a little bit better to get our hands on an a combinatorial interpretation of this. We're not going to quite get there. We're still kind of stuck on that thing, but we see that there's a program for helping us understand the combinatorics better and helping us understand the representation theory better in order to understand these coefficients. So the first thing I want to do is establish what H lambda tilde times H mu tilde is. Okay. Well, let me move this down a little bit. I'm going to set up a little bit of notation. So remember that an H tilde lambda occurs in our expressions as a multiset partition. So let's let it represent a multiset partition. So let's say that, that pi is a multiset partition of some set T, and m of pi is equal to lambda. And tau is a multiset partition of some set S, and m of tau is equal to mu. And I'm going to do this in such a way that so T and S should have nothing in common. So then I claim that H lambda times H mu is the sum over all multiset partitions of T union S, such that theta restricted to T is pi and theta restricted to S is tau. And then it's H tilde m theta. It says that there's a really pretty expression for the product rule in the H tilde basis. So let me do a small example. H2 tilde times H21 tilde. Okay, so I'm going to take my pi equal to 1, 1. And it doesn't matter which one you take, that I'm taking one where the multiplicity of the parts is 2, and then another one where the multiplicity of the parts is 2, 1. So I'm going to take 2, 2, 3. But any multi-set partition where this happens is fine. And then I'm going to have one term for every multi-set partition of their union. So 1, 1, 2, 2, 3. And I hope you don't mind if I stop drawing the curly braces around, because they're getting in the way and I'm not very good at drawing them. But 1, 1, 2, 2, 3. I can join a part of size 1 and a part of size with one of those. I can draw it 1, 2, 2, 1, 3. I can join two parts of size 1, 1, 2, 1, 2, 3, and 1, 2, 2, and 1, 3. And I say there's one term for each of these. So this is H221 tilde plus H1111 tilde plus H211 tilde plus H21 tilde plus H111 tilde. So the proof, it does only use what was already known in symmetric functions. And you take the Frobenius image and you say, you reduce it to Hn minus size of lambda comma lambda, Kronecker product Hn minus size of gamma, or size of mu comma mu. And the combinatorial interpretation in the literature for these objects doesn't look like multi-set partitions. What it looks like is this is so Z greater than or equal to 0 matrices and the reading word of, so the row sums need to be lambda, the column sums need to be mu, and the entries need to be the output partition, the right-hand side. And what I claim is that this interpretation in terms of multisets is equivalent to, you just find a bijection between the two. I'm sure there are other ways of getting at it, and perhaps if you had started from this perspective, you would have rediscovered this, this formula. But this is just a reformulation of what was of the Kronecker product of two homogeneous symmetric functions that has been in the literature. Okay. So my next one, what I do. So I want to be able to compute H mu tilde times S lambda tilde. That gets me closer to the Kronecker coefficients. And so I'm going to say that this has an expansion, and it has a combinatorial interpretation, and again, you're going to reduce to the known cases that are classical, and you can find the answer in McDonald actually if you do that reduction. So it's B lambda gamma mu S gamma tilde, where B lambda gamma mu is the sum over all tau 0, I'm going to say tau star, which is equal to, so tau star means I'm going to have tau 0, tau 1, tau 2, tau 3. So tau I is a partition of mu I. And we're going to take the Littlewood-Richardson coefficient, lambda, tau 0, tau 1, tau, say, L of mu, and then see gamma, tau 0, tau 1, tau L. Now, this is clearly a positive sum. If you want to take a combinatorial interpretation, you can. I actually need it because I want to use this expression and encode this as tableau. So the coefficient itself is clearly positive. It has a positive sum. I would say we don't have any problem saying that this is a perfectly fine combinatorial expression, but I want to put it into tableau. So we create sequences of tableau. Which encode this coefficient. So in order to do this, this is encoding two Littlewood-Richardson coefficients at the same time, and they are closely linked, right? So the tau 0 through tau L, those are the same for each of these two Littlewood-Richardson coefficients. So we want to create one object which encodes both of those at the same time. Sure, my phone doesn't go off while I'm. Right. So how am I going to do this? What I'm going to do is I'm going to use an object which encodes two different interpretations for the Littlewood-Richardson rule and kind of uses them in the same object. So what are my two interpretations of the Littlewood-Richardson rule? So one of them is that C, say 3, 1, 1, 2, 1, and then 4, 2, 1, 1 are encoded by the two objects on the top. This is the one where it's the outer shape is 4, 2, 1, 1. 4, 2, 1, 1, 4, 2, 1, 1. The inner shape is 3, 1, 1. And the filling of this object is something which, if you use jeu de taquin, goes to a shape, to a fixed tableau, not necessarily the super standard one, but it goes to a fixed tableau of shape 2, 1. So that's my first Littlewood-Richardson rule. And my second Littlewood-Richardson rule is I'm going to take, for the same coefficient up here, I place the shapes 3, 1, 1 and 2, 1 in skew form. So 3, 1, 1 and 2, 1 in skew form. And I fill it with the numbers with 4 1s, 2 2s, 1 3, and 1 4 in such a way that the reading word is lattice. That is, if I read from the bottom right to the top left, that reading word has more 1s than 2s, more 2s than 3s, more 3s than 4s, or at least as many 1s as 2s, at least as many 2s as 3s, at least as many 3s as 4s. So the reading word is 1 1 2, 2 1 1, 3 4, and at every single leftmost subword that there contains at least as many 1s as 2s, at least as many 2s as 3s, and at least as many 3s as 4s. This one here, 1 1 2, 3 1 1, 2 4. And I'm going to use both of these combinatorial interpretations for the Littlewood-Richardson rule in order to encode them in one object, which gives me that coefficient which appears in the product. So what I'm going to do is I'm going to make sequences of tableau. They are of skew shape. So the first one is rectified so that it is a partition shape. The next tableau is of skew shape, and the inner shape is the same as the previous one. Always the inner shape is the same as the outer shape of the previous one. What has to, the other condition is that at any one step, if you rectify it to jeu de taquin, that using jeu de taquin, that the shape of the partition, is your tau. So if I bring this to straight shape of 2, that it is of shape tau. So here's this is one where tau 0 is equal to 1 2 3 4 5 5 5 1 5 1. Tau 1 is equal to 2, and tau 2 is equal to 1. And then, of course, this is coming from the product of H21 tilde times S 4 tilde. It has a term. There are 6 of these. 6 of these. And the content is 1, 2, 3, 4, 5. 1, 2, 1, 2. So it's S22 tilde. Because remember, we get rid of that extra long row. So there are 5 extra ones. The number of ones is kind of flexible as long as it's huge. Just needs to be just big enough. We should also see this in H21 tilde times S22 tilde. Six S 4 tilde. Okay. And I claim that the number of these objects is this coefficient that I wrote back here. Nice and precise here. So the content of the tableau, of all of the tableau, needs to be equal to, say, gamma. I can interchange gamma and lambda. The outer shape, well, content of it needs to be not gamma, but n minus gamma comma gamma, n minus size of gamma comma gamma. The outer shape of the tableau, like the last shape, needs to be n minus size of lambda comma lambda. It's not clear that these two things, that you can interchange the content and the shape in the end. So it's not a symmetric object, yet the coefficients are symmetric. And then the sizes of the skew tableau are so mu 1, mu 2, and so on, mu L. So the object that I'm getting, oops, I wanted this to go here. Okay, so this one is of size 2 and this one is of size 1 because we're multiplying by H21 tilde. And now I've got this as a sequence of tableau. I can record it in a single tableau by kind of overlaying these on top of each other and putting restrictions on the entries in these sets. And so what we do is we record them as a multi-set tableau in such a way that it is recording the Littlewood-Richardson coefficients. I should note that there's this intermediate condition is that if you read the tableau this way, that the reading word must be lattice. So we add that condition. If you do this, the reading word from the first tableau, second tableau, third tableau, the reading word needs to be lattice, and that will encode that 2 lattice conditions at the same time. One of them is encoding it in a skew tableau, the other one's encoding it in the lattice reading word. Okay. Now, what we do is we record the the coefficients as a multi-set tableau, and we put all of these different conditions on it, but it's easiest, so, and it's really hard to remember all of the conditions on the multi-set tableau, but if you remember that they correspond to these objects, right? And these objects are going to be encoded as a single multi-set tableau, because that allows us to look at repeats of these objects, right? Because we have multiple we're going to have in a general expression involving h mu tilde as lambda tilde. If we have a coefficient here, we need to have multiple copies of these things. So how are we going to represent multiple copies of them? Is we're going to have one for every multi-set partition that appears in our expression. So let me give the correspondence between these multi-set tableau that I've drawn here and the object that I had before. So I'm going to take this one just as an example. And I'm going to say, the way I'm going to read this is I'm going to put in a total order on the multi-sets, and I'm going to insist that these multi-set tableau be column strict with respect to that total order on the multi-sets. And then within that, the barred entries. And so the first one I record, so it has no unbarred entries. So the shape looks like this, right? Because the no unbarred entries are just these entries. Now, how am I going to fill it? The blank entries count as one. So I'm going to always, wherever I say blank entry, I'm going to fill it with ones. Wherever I have 1 bars, I'm going to replace them with 2s. So my next one, I'm going to look at all of the entries which contain the multi-set 1. So I look at the ones that contain a multi-set 1, and they're in a skew tableau. And they only occur in this cell and this cell. And I'm going to fill those with 3s. And then the last one, I look at the multi-set tableau, and the last entry I'm going to look with multi-sets 1, with multi-set containing 2. So that's this guy, corresponds to this cell. And because the 2 is with nothing, blank cell counts as a 1, an extra 1, because you can have as many 1s as you want. And that's the correspondence between these multi-set tableau and these objects here, which I claim represent the h mu tilde times s lambda tilde coefficients. So I'm just giving you the idea of how of where these combinatorial interpretations come from, but let me show you the exact conditions on these multi-set tableau. Okay. So I'm going to take h mu 1 and multiply it by h mu 2 and h mu l. Using my product rule, this is going to be the sum over all theta, which are set partitions of a multiset one to the mu1, 2 to the mu2, L to the mu L. And then H tilde M of theta. Now compare this to H mu1, H mu L. And this is the sum over theta, which are multiset partitions of 1 to the mu1, L to the mu L. And there's one other expression I want to consider, is that S mu1 tilde, S mu L tilde. But for this, you need to know that SR tilde is equal to HR tilde minus HR minus 1 tilde. So this is going to be the product of S mu1 tilde minus S mu1 tilde minus 1 and S mu L tilde minus S mu L tilde minus 1. And so you can say, oh, well, this is an inclusion-exclusion. So this is going to put an inclusion-exclusion condition onto my tableau. And then this is, whoops, those should be H's. H mu. And this is H mu1 minus the indicator of 1 in S tilde. H mu2 minus the indicator of 2 in S. And H mu L tilde, tilde on the H, not on the mu, minus L in S. Hope that's readable. Okay. So here we're saying in my expression of a product of H tildes, I have one multi-set partition. One set partition of a multi-set for each of these. In this one, I have one multi-set partition of these. And in this one, I have set partitions, but then there's an inclusion-exclusion. Oops, there should be a sign in here. -1 to the size of S. There's an inclusion-exclusion on the products that are going on here. And so what I want to say is that I claim that I have come up with a combinatorial interpretation for the following products. S1, S mu1 tilde. S mu L tilde times S lambda. And the coefficients are dominated by, and that's what I'm going to use the less than or equal to represent, H mu1 tilde, H mu2 tilde, H mu L tilde times S lambda tilde. And the coefficients are again dominated by H mu 1 tilde, H mu 1, H mu 2, H mu L, S lambda tilde. How do I do that? I base it on the combinatorial interpretation for H mu tilde times S lambda tilde. Is that I've given a combinatorial interpretation for this in terms of these tuples of tableau. Then here there's one tuple of tableau for every multi-set, every set partition of a multi-set. So the combinatorial interpretation here is based on the combinatorial interpretation here. The combinatorial interpretation here is based on the same thing, right? We say there's one multi-set partition of a multi-set for with a term that looks like this, and then we have the combinatorial interpretation for that element based on this. But what's amazing is that you can also get this one here. This here puts a restriction that the first row may not be filled with singletons. I don't want to go through all of the tedious definitions that are in the paper because they you almost have to unravel them to understand why they're true. But the unraveling is all based on this one combinatorial interpretation for the coefficients of a product of an H tilde times an S tilde. And it allows you to then give the combinatorial interpretation of this, because this is positive in the H mu tildes, and so we know the product. And again, this is so the product of the H is positive in the H mu tildes, so we have an interpretation for the product. This one here is Mobius inversion, so I believe that it turns out that there's a combinatorial condition that you can place on the tableau, which captures exactly the Mobius inversion. Okay. I will say that contained in this last one is the product S mu tilde times S lambda. It is dominated by. The question is, how is it dominated? What is that extra condition that you need to place on these tableaux in order to get these tableaux? It's some extra lattice condition. We've tried the obvious lattice condition and it didn't work the way we had hoped, but I believe that there is one that is not far away. And I say not far away. I'm not actively working on this one. I'm working on a different, really hard combinatorial representation theory problem. But this one must be positive in this. And this one is dominated by S mu times S lambda tilde. And its expansion in the S tilde basis captures the restriction problem. So here we have the restriction problem, here we have Kronecker, and here we have them connected. And I believe that the place to resolve all of these questions lies in multisets tableau. Okay. I want to stop and ask if there are questions. This is my ask me anything about Kronecker and reduced Kronecker, because this is where I think it helps to know what other people want to know.
Thank you, Mike. Let's thank the speaker. Any questions? See. I don't see any. I don't
I have
see
a
any question yet. Okay.
Sorry, I don't know if you can hear me. I'm having trouble with my
Yes.
audio. And this is Sheila. I was
Yeah.
just wondering, is there a known way to do this by some insertion scheme?
Working on it.
Okay. Okay.
I'm not saying it may be impossible to do it with an insertion scheme, but the ideas that are coming from the symmetric functions, I'd say, lead you to the idea is that, oh, there should be a way of doing this restriction inside of this restriction using an insertion scheme. It is definitely too naive to think that the obvious things work, because I've tried all of those, but I was naive. I'm now getting smart about how it must be done.
Yeah, no, I'm sure it's very difficult, but I was remembering a very old paper of Glanford Thomas, where he does, as I recall, a very beautiful proof of the Littlewood-Richardson rule by inserting one standard tableau into another. So this reminds me a little bit of that.
See, maybe that's what exactly the things that we need. We need to apply them to in the right way, and maybe apply them with these new objects.
Thank you.
Sheila, can you repeat the name of the person, please?
Yes, it's a Welsh name. So the last name is Thomas, and the first name is, all right, I'll try and spell it. GLANFFRWD, if I remember correctly.
Thank you.
Sure.
All right. Any other questions? If not, then let's thank Mike again. And I will see everyone on Thursday. Bye. Thank you, Mike.
I see you.
Thank you.
Bye bye, Mike. Thank you.